Hello guys, so welcome back to our lecture 5. Basically, this is the last part of lecture 5 and also the last piece of physics that we're gonna study regarding the diode physics or the beam junction physics. Henceforth, we're gonna just apply what we learned in physics into circuits. Okay, and this last piece is all about the breakdown in reverse bias. So basically, what we learned so far is that when the diode is reversed, I mean we apply a reverse bias condition. Okay, when we connect a battery, this battery has a positive terminal connected to or closer to the N region, and the negative terminal of the battery is closer to or connected to the B-type region. Okay, or the voltage of the N-type terminal is larger than the voltage of the B-type terminal. Okay, then the diode is reversed or the beam junction is reversed. Okay, and we see that the built-in voltage enhanced, the depletion region become wider. Okay, and this will improve the ability, we can say, of the built-in potential to prevent the hole crossings from B to N and the electron crossing from N to B. And that's basically stops the current and makes it very small just because of the minority carrier current or motion. This minority carrier motion, we learned that they are moved basically across the junction. So the electrons in the B-type region goes and cross the function to the N-type region because they are attracted to the positive terminal of the battery, and the holes in the B-type region in the N-type region goes and cross the junction to the B-type region because they are attracted to the negative terminal of the battery. This will create a very small current, which is IS. Okay, but if the reverse bias voltage, the battery voltage, which is reversed now, goes beyond some amount, usually between 5 and 8 volts, sometimes 10, but this amount, which we call the Zener breakdown amount or the Zener breakdown voltage, will be high enough to free electrons from their bonds. So basically, if you remember, guys, that electrons in the valence band to go to the conduction band, they need energy. Okay, till this moment we talked about thermal energy, that if the electron gains enough thermal energy larger than the energy gap, it can go from the valence band to the conduction band. But it's not only the thermal energy, it may be electrostatic energy. I mean energy that came from electric field. Okay, and that's exactly what the reverse bias voltage can do. So it can reach some amount. This amount is high enough so that the electrons or the atoms, the electrons that are in the bonds right now can gain energy and become free from their bonds and go to the conduction band. Okay, so that's basically what happens here. So as you see, guys, here, these electrons here are free due to this reverse voltage. So in that case, the reverse here is larger than or equal to what's called the Zener breakdown voltage, which usually small, maybe 8, 15, something in that range. Okay. And we noticed that when we reach such amount of reverse voltage, okay, the voltage drop across the diode becomes almost constant, and only the current that increase. Okay, good. The other type of breakdown is called avalanche breakdown, and this is very interesting one. Okay, some other diodes, okay, can break down at very large amount of reverse voltage. Okay, but this is interesting because since it's a large amount, maybe tens to hundreds, maybe 30, 70, 100 volt reverse, this is very large, maybe tens or hundreds of volts, 100 volt, 150, something like this. Okay, at least tens, 20, 30. So that amount of, again, electrostatic energy, okay, when one of the minority carriers, like for example electron, gain such energy, it moves with a very high momentum, very high speed. So it has a very high momentum. So when it impact or when it collide with an atom, silicon atom for example, it may free, more than one electron as well. So basically here again, the electrons tend to move from the valence band to the conduction band. Okay, so it needs energy. This energy can just come from the electrostatic energy, like to be free, like Zener breakdown. And in avalanche, we will have both. We will have, the electrostatic energy, so electron can just be free and go from its bond and go to the conduction band. And also, when the minority carriers moves across the junction, okay, they will move with a very high speed because there are very high electrostatic energy applied, which is, this reverse voltage. So they will have a very high momentum. So when it collides with an atom, okay, the energy will transfer from that electron to that atom, to the electrons of that atom, so they can also be free. And usually such collision result in multiple electrons to be free at the same time. So let's, for example, assume we have a silicon atom like this, which is connected to the surrounding with four other silicon atoms. Okay, then an electron just collides with a very high momentum. Momentum is mv, mass multiplied by speed. So this collision might result in something like this: silicon, and maybe these two electrons will just become free. Maybe just one from here become free. Maybe another one from here become free. Maybe also the one from here. So one electron result in 5 free electrons. 1 to 5. M here, I called this M, the number of free electrons is 5. Okay, and remember, those 5 electrons that will be free now are now free in the conduction band, and we have the same high reverse voltage, so they will gain high energy. Then they continue moving, colliding with other atoms, free other electrons, and so on and so forth. That's why it's avalanche. It's very big. Okay, so one atom, one electron can result in more than one free electrons, and each one of those result in more than one free, and so on and so forth. Okay, and in the avalanche breakdown, also the first, kind of breakdown is also valid. I mean, also this high energy applied, high reverse voltage, can also free some electrons from their bonds just without any collisions. So we have both. But this effect is much bigger than the first one. Okay. So what is this? What is the effect of this on our characteristics between I and V? Okay. So let's draw the characteristics after applying this. If there is no breakdown, the characteristic will be something like this. Let's draw it with red. In forward, there will be no change. In reverse, before breakdown, there is no change. Then after breakdown, okay, we will have such a thing here. So the current increases in that way. It's still negative current. Okay. and the voltage is almost constant, equal to the breakdown voltage. And this breakdown voltage is a characteristic to the diode. You may buy a diode, look at the data sheet or the manual, you will see that breakdown voltage. The ideal characteristic, if there is no breakdown, it should be something like this, just to continue. That is in case no breakdown. Between brackets, this is ideal diode. The ideal diode should be like this, with no breakdown. So let's now, summarize the whole picture, okay? So we have a relation between I and V, that this relation is ID equal to IS exponential VD over VT minus 1. And you can, neglect minus 1, that's fine. So in forward bias, in that part here, this is the forward bias. Both ID and VD are positive, and we can use this relation. Actually, this drawing came from this relation. In reverse bias, okay, when VD is much larger than, as a magnitude, VT, we will have a current almost equal to minus IS or minus I naught. And this also comes from this relation. Just put VD, for example, equal to minus 10 VT. VT will go to with VT, so it will end up with IS exponential minus 10 minus 1. Exponential minus 10 is just 0. Just make it in your calculator, it will be just 0. And ID will be equal to minus IS. Okay. Until the breakdown, then at that point we cannot use this relation again. So at breakdown, we cannot use this relation. Basically, if you apply it and you put VD equal to minus V breakdown, it will give you minus I naught still. That's why I call this ideal diode. I mean, the relation will hold forever in breakdown, and that's wrong. At breakdown, how to deal with the P junction? That's easy. Its voltage approximately equal to, it doesn't change a lot. It changes, but with very small changes. So we'll consider it equal to minus VBD all the time. So we know the voltage across the diode, it's minus VBD. Then based on that and the rest of the circuit in which the diode is connected, we gonna determine the current, which is ID, as you will see later. Okay, so starting from next lecture 6, okay, we're gonna review our characteristic, IV characteristic. Then we're gonna start apply it in circuits, and see possible ways to solve diode circuits. Okay, thank you very much, and see you next time. Bye bye.